All right. So we're starting with example 5. All right. So this one is the integral from 0 to 5 of 2 to the x dx. 2 to the x dx. And this is where I get out my yellow sheet because I'm like, I don't know what that integral is. What in the world? Do you guys have your yellow sheets handy? Anybody? I'm like, I don't know. Mr. Rice, I don't know. I don't have it memorized yet. This is about the time in the year where I start to really depend on my yellow sheet because it's a lot of memorizing, yeah. Okay, so when I integrate something in the form of a to the x, what is it? What's the antiderivative of a to the x? Yeah, it's a to the x over ln a. So this is going to be 2 to the x over ln 2. And then we're evaluating it from 0 to 5. This is where like flashcards really come in handy. I made it. I typed it up myself. Oh, it's on the integral side, and it is, hold on, I shall tell you, it is number 5 on the integral side. All right. So we've got 2 to the 5th over ln 2 minus 2 to the 0 over ln 2. So we do have a common denominator of ln 2, so I guess that's cool. And then what do we have as a numerator? $31, yeah. So 2 to the 5th is 32. 2 to the 0 is 1. So 32 minus 1 is 31. Yep. Calculus is full of ugly answers. So, I mean, everyone's beautiful. Everyone is beautiful, and this number is beautiful. So, all right, number 6. Yep, this is a U substitution problem. Can you recognize what the U should be? Say it again. I think you were right. I just wasn't sure if I heard you correctly. Yeah, it's the bottom, yeah. So, and that's because we know from the video last night what to do with a 1 over U now. So we're gonna say the bottom is the U. All right, so we've got U equals 1 plus 3 to the x. And then that means that the derivative of U, so we're going to take our yellow sheet, flip it back over. The derivative of U is what? The x ln 3 dx, okay. And in the problem, we do have a 3 to the x, but we don't have the ln 3. So we're going to divide that over. Okay, so the problem that we are integrating is 1 over ln3 times the integral of 1 over u du. Okay, when we integrate 1 over u, what do we get? Okay, so we get 1 over ln3 times ln u plus c. Okay. Okay. And then what do we do with the top? So we're going to say this is ln 1 plus 3 to the x. All right. How your brains feel? Feel okay? Okay. We're going to do one more, and this one is going to explain what is on your, this one you could kind of add. This one you could maybe add to your yellow sheet actually, because it's not already on there. And it feels like it should be. But if you look, nowhere on your yellow sheet does it say how to do the integral of tan. No, it does. This is the explanation for how you do the integral of tan. So if you look at this one, if you look at your yellow sheet, instead of the integral of tan being something like some regular trig function, it's like funky. And you wonder, like, why? Because you'd think that it would be something normal, right? Like when you look at like integral of sine, integral of cosine, integral of secant squared, cosecant squared, all those are kind of normal, and then you get to the integral of tan and cotangent, and they're like weird, and it does not really make sense. So right now what we're going to do is a proof of how you do the integral of tan, so you guys can see where it comes from. Okay? Sound good? Right. So if we look at tan, the reason that the integral of tan is weird is because we never had something when we were doing derivatives where the derivative of a trig function was, oh, I take the derivative of that and it gives me tan as an answer. Does that make sense? So there wasn't something where it was just like a clean, oh, derivative equals tan. So when we take the integral of tan and we try to do the antiderivative and go backwards, that means there's not going to be a clean answer for that either. So what we have to do is we have to take tan and we have to rewrite it as a quotient so that we can actually take the integral of it, and that's what's going to make it messy. So when we take tan and we rewrite it as a quotient, what would the quotient be? It'd be sine over cosine. Which means we just took it and we turned it into a U substitution problem. Okay, which is why we didn't do it before today. Now, we didn't do it yesterday because we didn't have the tools to handle it yesterday. So if we're doing it today, that means that we have to use ln or e or a to the x or something like that to do it. So where is the u in the problem if we're doing it today? Is it going to be sine? So think about how u substitution works, right? You choose a u, and when you choose the u, the derivative has to be there, right? So if we think about it, if you chose, because the way that it works, we know, like there was a problem yesterday where there was a sine and a cosine, they were next to each other multiplied, and you could do the problem two different ways. So that was an interesting problem. But if you think about it, if you chose sine to be the u on top, the derivative of sine is not a cosine on the bottom of a fraction, is it? Right? So we could not let sine on the top be the u, because there'd be no way to get the cos on the bottom. It would have had to be on the top as well. So the only way to do this problem is to make the u be the cos on the bottom. Does that make sense? So when you're doing u substitution, it's not just important to make sure that you have the u be kind of like the inside. It's also important to consider that when you do the derivative shows up, and it shows up in the right place. Does that make sense? Okay, so we're going to say the cos has to be the u, because the derivative of cos is sine, or negative sine in this case, but the derivative of cos is something that can show up on the top of a fraction and be correct. Does that make sense? The derivative of sine is not a cos that's on the bottom of a fraction. That just can't happen. Okay? So we're going to say the u has to be cos x, and then the derivative of u is what? Negative sine x. Okay. Now, we don't have a negative, so what do we have to do? Yeah, divide the negative over. So negative du equals sine x dx. I would say we are kind of getting to the point in calculus where we can't make blanket statements like that, where you're going to have to think through something and make sure that it works rather than say, oh, this is going to work every time. So I can tell you, oh, something's going to work 99% of the time, but there's going to be that 1% where you're going to be like, Miss Rice, you led me astray, and I'm going to be like, I'm sorry, it usually works. You know what I mean? So we're officially to the level of math where you're going to have to think about the problems as you do them, and you cannot shut off your brain and go on autopilot anymore. Does that make sense? That's the level of math that we're at now. When else would you have a 1 over something when it wasn't an ln, you mean? It's just that calculus does not follow perfect patterns. So, for instance, yesterday we said, oh, the u substitution, it's the inside versus the outside, and then we got to the end and there was one problem where we were doing the u's and then there was a leftover x in the problem. So all the problems tended to work out to the same, and then I found the one example where we were like, we did u substitution, there was still an x in the problem. What? And were those the common problems? No, but there were a few of them at the end of the assignment. So they're not everything, but they do show up. Does that make sense? So if I made a blanket statement that it works out every time, then you would have been like, Ms. Rice, you're wrong. Because we can, in the textbook, when they give you 150 problems in the textbook, maybe the last 50 are like that, we just never assign those 50. Does that make sense? So it's like, there's always the more difficult problems that maybe in high school we don't touch, and then you get to college and you're like, Ms. Rice lied to us. Because she just didn't realize that they didn't assign, we didn't really assign those problems in high school, and I just didn't even know, that those problems were out there. So sometimes just because I can't come up with an example off the top of my head, I have a hard time as a calculus teacher making blanket statements because there are always exceptions to the rule, it seems like. Yeah. In lower level math, they protect you from it. They do really nice problems, and then when you get into higher level math, they start to let you guys see them, and then you realize that math is not the subject where there's always a right answer and everything is always clean. Then you start to realize there are lots of ugly answers, and there are some problems where we don't know what the answer is, and if you can debate the answer and defend your answer the best, then you're the one who's right. So it starts to maybe feel like math is a little bit more like English, where it's just a game of arguments. You know what I mean? So Yeah, it's hard to say that it's going to do that every time. Now, we'll find out that basically what happens in math is you start to realize there's like strategies, and some strategies work more often than others. So you'll be like, this is my strategy 95% of the time, so I will default to this strategy because it seems to work a lot. And then when it leads me astray in that one problem, I will go to my second favorite strategy. And I will just work my way down the list of strategies until I find the one that works. And then if the problem makes me cry 5 times in a row, I throw that problem against the wall and I move on. You know what I mean? Like that's just cut my losses and let it go. So I think it kind of depends on the problem, how dedicated you are, how much that problem made you mad, how much you care about the grade on that particular assignment or whatever. That's kind of where it goes. Yeah. Does that make sense? Okay. All right. So what should we do next? Where are we at? Okay, so we got the negative in the front. We got the 1 over u. Oh, so I was saying I've got these two are the negative du. Okay, so that's what I've got. So I got negative 1 over u du. And when I integrate that, what do I have? Got negative ln u plus c. Okay. All right, so let me go ahead and take the cos, plug it back in for the u. Now, let's compare this with our yellow sheet. Is this what our yellow sheet says? No. So how did they get that? What? Okay. Well, we're going to compare it. So now we're going to use property of logs because ln is a log. It's log base e, so properties of logs apply. So when there's a negative in the front, what number is the coefficient if it's just a negative? It's a negative 1. And with property of logs, what does a number in the front mean? It's an exponent. It's an exponent. Okay, so this is ln of cos x to the negative 1 power, right? Right? And that's 1 over cos. And 1 over cos is, there we go. Now, negative ln cos x plus c is not a bad answer. That's a good answer too. But this is where ln secant x plus c comes from. Okay. Does that make sense? So if you look at your yellow sheet, can you imagine where the ln sine u plus c comes from? Yeah, same sort of proof. Okay. All right, that's all I have for you today. So if you look at the assignments, it is the punchline sheet and then 2 problems from Larson. All right, sound good? All right, I'm going to work on grading your quizzes. Remember, we do have a test the day before Thanksgiving break. Are we all still planning on being here? Yes. Marvelous. Okay. There was a little bit, they got a refurbished toner